Okay, hello everyone, it's Salar and we are in part 53 of our tutorial, a tutorial to writing a real-time operating system. Developing a real-time operating system. In previous part, I did the implementation of WaitList for the RTOS, and I said by using a thread wait system call, you can make a delay. But in this part, I want to start talking about semaphore. I want to talk about concept of semaphore, concept and structure of semaphore. And in this part, I don't want to implement semaphore. I have no plan to implement the semaphore in this part. But what is semaphore? Talking about semaphore, first let's see an example. Assume you have two threads, thread 1 and thread 2, and here is thread function of thread 1 and here is thread function of thread 2. And in these two functions, by using of serial port print, you want to print a number in output. In a normal situation, when you run the code first, the operating system, for example, run thread 1, and in this function print this number in the output. Okay, 6 1. Okay, the number of 1 is 6. Okay, and after that context switch to thread function do and print this number. Okay, in a normal way and in a normal situation. But assume an abnormal situation. Assume in thread function 1, after printing these two 1 and 1, you have a context switch and RTOS jump to thread function 2, and in this function print this number, and after another context switch return thread function 1 and print rest of the string. Here is a abnormal situation, and this abnormal situation called conflict between thread 1 and thread 2 when using a shared resource. Serial port is a resource that has been shared between thread 1 and thread 2. When you using shared resource, when you share a resource between some threads or two threads, you may have conflict. Okay, but what can we do to get rid of these problems, to get rid of conflict when using shared resource? By using of a locking mechanism, you can get rid of this problem. For example, in this example, another time you want to print two numbers in the output, but before using this resource, the thread must acquire the resource by using of this function, lock function. After running thread function 1, the thread must run this function if thread wants to use this shared resource. Lock serial port. If serial port is free, the return value will be okay. Okay, assume first RTOS runs thread 1. Thread 1 wants to use serial port, so use this locking mechanism, this lock function. And at the first, serial port is free. So the return value of this function is okay. And because the return value is okay, thread function 1 can acquire the serial port and print its number in the output. But assume after acquiring the serial port, at this time, after printing 1 in the output, you have a context switch and RTOS jump to thread function 2. Now, another time, thread function 2 must acquire this resource by using of this locking mechanism. But because serial port has been locked by thread 1, the return value of this function is error. Okay? And thread function 2 can't acquire this resource and can't run this line of code. So after another context switch, another time, RTOS jump to this instruction, okay, and print other ones in the output, okay, and you have no conflict in this example. If thread function 2 wants to print this number in the output after unlocking the serial port, thread function 2 can acquire and can get this shared resource. So to preventing these situations, abnormal situations, these conflicts, you must use locking mechanism. When you want to use a shared resource, first you must lock that resource. If locking is successful, use the resource. After using the resource, another time unlock the resource. Okay? But serial port or USB or even a global variable can be a shared resource. And semaphore is a locking mechanism. So what is semaphore? A locking mechanism. And when using shared resource to prevent conflict, abnormal situations, locking mechanism must be used. By using a semaphore, you can prevent conflicts. By using a semaphore, you can prevent conflicts. But how we can implement semaphore or a locking mechanism? By a simple variable. When you want to use this shared resource, first you must check this variable. If the value of the variable is 1, means resource is free. When the value of semaphore is 1, this means resource is free. After, if the resource is free, the value is 1, you must lock the resource. 0 means lock. After this line, the resource has been locked. You can use this resource, and after that another time unlock the resource by putting the value of 1 in the semaphore. In this way, easily you can implement this locking mechanism by using a variable. But semaphore related to a resource. For example, at this time, semaphore related to serial port. Okay? And I said serial port, USB, or even a global variable is a resource. But sometimes the count of a resource of one type is more than 1. For example, assume you have 4 USB port on your board. Each USB port is a resource, but you have 4 USB ports for resource of one type, for single type resources. In these cases, semaphore count determine the number of resources. For example, in this example, we have just one serial port. The value of semaphore, the maximum value of semaphore is 1. If you have more resources, you must increase this value. Assume you have another time 4 USB ports on your board. The value of semaphore shows the number of free USB on your board. For example, when semaphore is 4, you have 4 free USB on your board. When semaphore equal to 3 you have 3 free ports on your board. When semaphore equal to 2 you have 2 free ports. When semaphore is 1 you have just 1 free port on your board. And when semaphore equal to 0 you have no free port on your boards, and all of USB ports has been used, okay? So now I want to implement a countable semaphore, okay, or a counting semaphore. When the number of semaphore, the maximum count of semaphore is 1, it's called binary semaphore. But when this value, the maximum count, is more than 1, it's a counting semaphore, okay? It's a name, it's not important. But how you can acquire a semaphore? If the value of semaphore is greater than 0, this means you have at least 1 free port. When the value is greater than 0, you can acquire the semaphore by doing semaphore minus minus to acquire the semaphore. After that, you use the shared resource. Another time you must unlock and release the semaphore by using of semaphore plus plus. If the semaphore count is equal than maximum count, okay, because the maximum count of semaphore is 4. Okay, so in this way you can implement counting semaphores. But in our RTOS, I want to implement the locking function by using of this system called semaphore get, and unlocking function by using of semaphore release to acquire a semaphore and release that. Here is locking function, here is unlocking function, unlocker function, locker function and unlocker function, or system call. By using of system call get, you can get a semaphore for a thread, okay? And I get into timeout in next slides. At this time, timeout is not important. It's like a delay, okay? And by using of semaphore release, you can release a semaphore. ID is ID of semaphore, okay? Each semaphore, like a thread, has an ID, okay? When you want to acquire a semaphore, you need the ID of semaphore, and when you want to release a semaphore, you need the ID of semaphore. So in this way, you can use semaphore get and semaphore release. When you want to use a shared resource, you must get the resource by using of semaphore get. This is idea, that semaphore that you want to acquire, and after that release by semaphore release. And if the return value is okay, you can use the shared resources, the shared resource. But let's see this situation. What will happen if, when a thread wants to get a semaphore, the semaphore count was 0? You have no free resource. No, you have no free resource in this situation, because the count is 0. When the count is 0, semaphore count is 0, you have no free resources. Okay, but what will happen if, when a thread wants to get a semaphore, the semaphore count was 0? In this situation, RTOS inserts thread in the wait list, okay, as much as timeouts, If the count is 0, RTOS puts thread in the wait list as much as timeouts. But if before running out or elapsing the timeout, okay, if before elapsing the timeout, elapsing this delay, for example, assume this delay is 500 milliseconds, but before elapsing this delay after 100 milliseconds, if the semaphore is released, another thread, for example, assume thread 1 wants to get the semaphore, but the value of semaphore is 0. RTOS put thread 1 in the wait list as much as the timeout, for example, 500 milliseconds. But if before elapsing this time, for example, after 100 milliseconds, if the semaphore is released, okay, if another thread, for example, thread 2, release the semaphore, in this situation, RTOS will get semaphore for the waited thread, for thread 1, because thread 1 waited for semaphore as much as 500 milliseconds. Get semaphore for the waited thread 1, and return thread 1 to ready list after, for example, 100 milliseconds. Otherwise, assume no other threads release the semaphore, no other thread releases the semaphore until to the end of this delay, this timeout, no other thread releases the semaphore. The RTOS returns thread 1 to the ready list, from waitlist to the ready list. But at this time, by using of kernel waitlist handler, like a simple waited thread. But semaphore get will have resource error in return value. You will have error, okay, if until to the end of this delay no other thread releases the semaphore, you will have error in the in return value of semaphore gets. And thread will not be able to acquire the semaphore and will not be able to acquire the resource. So you need to have this value, this delay, this timeout in semaphore gets, because when the count of semaphore is 0, RTOS puts thread in the waitlist as much as timeout. Now let's talk about semaphore release, this system call. To releasing semaphore if the count of semaphore was 0. If the semaphore count is 0, RTOS will return most prior thread. Most prior thread. Let's do another time. Return to this slide. I said if a semaphore releases, if a thread releases the semaphore, RTOS will get semaphore for the waited thread, for the most prior waited thread, because sometimes more than one thread, for example thread 1, thread 3 and thread 4 have waited for a semaphore, because sometimes more than one thread have waited for a semaphore, and by releasing a semaphore which its value is 0, RTOS will get semaphore for the most prior waited thread. If the count is 0, there may be some threads that's waited for a semaphore. Okay, RTOS will return most prior thread to the ready list if exists, and allocate semaphore to that thread, most prior thread. Otherwise, if there are no thread waited for a semaphore, okay, if no other thread waited for a semaphore, semaphore release just increase the value of semaphore count. Just increase the value. Okay, but how does the RTOS find the most prior thread that's waited for a semaphore? By using of semaphore waitlist, another list or data structure that's been used in the RTOS. But what is semaphore list? List of threads that waited for a semaphore. I said sometimes more than one thread waited for a semaphore, that its count is 0. Semaphore waitlist is a list of thread that waited for a semaphore, but semaphore waitlist is a binary tree. Okay, this data structure is a binary tree, and you know binary tree is a ordered data structure. Like here, and all of threads have been ordered in this data structure by using a thread priority. For example, assume this is thread 1, this is thread 2, this is thread 3, and this is thread 4. The most right node has highest priority in this waitlist. And at this time, thread 1, thread 2, thread 3, and thread 4 have waited for semaphore. Okay, but when RTOS want to return most prior thread, at this time return thread 1 because thread 1 has a higher priority than other threads. Okay, so by using of this data structure, RTOS can find the most prior thread that's waited for a semaphore. Okay, so RTOS will return most prior thread from WaitList to the ready list if exists and allocate semaphore to that thread. Otherwise, if this list is empty, no threads waited for semaphore, just increase the value of semaphore. Another time, semaphore gets. When a thread wants to get a semaphore, if the count of semaphore is greater than 0, just acquire the semaphore and use the shared resource and uses the shared resource and will use the shared resource. But if the count is 0, RTOS will put the thread to the wait list as much as timeout. If before elapsing the timeout another thread releases the semaphore, RTOS return most prior thread to the ready list. Okay, and get the semaphore for most prior thread. Otherwise, if no other thread releases the semaphore, return the thread to the ready list by using of kernel waitlist handler, like a simple waited thread. But at this time, the return value is error, and thread will not be able to acquire the semaphore. And for semaphore release, if the count of semaphore is greater than 0, this means there are no threads that have waited for a semaphore if the count is greater than 0. Okay, in this situation, just do count plus plus, just do count plus plus. But if the count is 0, RTOS will return most prior thread to the ready list if exists by using of this data structure. Okay, and otherwise, if there are no threads in the wait list, semaphore wait list, just increase the semaphore count. So semaphore is a locking mechanism, locking or signaling mechanism. If I want to be more exact, semaphore is a signaling mechanism. But if you want to know what are the differences between locking and signaling mechanisms, just search on internet. Okay, search on internet. You will find a lot of topics about differences between locking mechanism and signaling mechanisms. A semaphore is a locking mechanism or signaling mechanism. Semaphore is a signaling mechanism. If I want to be more exact. But for example, mutex is a locking mechanism. Okay, I will talk about mutex in future parts. But the concept is important. Okay, the concept is important. Concept of locking mechanisms and signaling mechanisms are the same. Okay, it's similar. So this part was introducing the semaphore, but in next part I will implement the semaphore, okay, for the RTOS. Okay, thank you very much to see me, and see you soon in the next part. Thank you very much.